So we know now that isomorphisms compare the properties of elements and subgroups that are in fact the same as one another. And in our previous video, we saw that one important source of how to create isomorphisms from a group to itself is to define them via conjugation by an element. We call those inner automorphisms. So what we want to do in this last video to wrap up is to take a broader look at isomorphisms that a group has with itself. Where do they come from? If they don't come from inner automorphisms, what other possibilities are there? And not only that, how do those automorphisms themselves behave as elements of a group in their own right? So we call any isomorphism from a group to itself. We give it a name. We call it an automorphism. Auto meaning the Greek word for self, right? So an isomorphism of me to myself is what we call an automorphism. And in our previous video, we saw that for any element in my group G, the function that I get by conjugating elements by A, so multiply by A on the left, A inverse on the right, that's the composition of the left and right actions by A, that will always give me an automorphism of G. We call those automorphisms inner automorphisms because they came from within the group by building them out of these left and right actions by an element of the group. But not all automorphisms arise in this fashion. And so those that do not, those automorphisms of a group that don't come from conjugation by one of its elements, we call those outer automorphisms. So every automorphism is either an inner automorphism because it's made in this fashion, or it's an outer automorphism because it can't be entirely created just by this virtue of conjugation. So what can we say? We can say for sure that the identity function is an automorphism of G. That we saw a while back, several videos ago, when we proved that the identity function is always an isomorphism. Now that we have the word automorphism, we can also associate that word with this too, right? Because the identity function associates a group to itself. So the identity function is an automorphism. We also know that if I have any automorphism from a group to itself, that its inverse will also be an automorphism. Why? Because a couple videos ago, we saw that the inverse of an isomorphism is again an isomorphism. And so when the two groups involved are in fact equal groups, G to itself, that means the inverse of an automorphism will be an automorphism. And finally, we can also guarantee that the composition of two automorphisms will again be an automorphism. So if phi is an automorphism from G to G, and psi is another automorphism from G to G, then when I do phi composed with psi, I will get an automorphism from G to G. And these three observations sound an awful lot like, respectively, the identity, inverse, and closure properties of a group, namely the group of automorphisms of G, where the operation is composition. And that is indeed a group, and it's a group that we call the Automorphism Group of G, and we'll denote it by AUT-G. A whole lot of really interesting abstract algebra is powered by the study of automorphism groups of a group, including, but certainly not limited to, the Galois theory of the roots of polynomial equations, which you can see a whole playlist of videos of me talking about those elsewhere in my YouTube channel. So I just want to wrap up this series about isomorphisms by looking at some examples. Not only of inner automorphisms, because inner automorphisms are always an important source of where automorphisms come from. In fact, they actually form a subgroup of the Automorphism Group of G. But in more generality, what else can we say about the automorphism group of something? So let's wrap up by quantifying what is the automorphism group of Z mod 6, the additive group mod 6. That's really just asking the question, if I want to create an isomorphism from this additive group mod 6 to itself, what are the different ways in which I can do that? So, first of all, we know that since Z6 is a cyclic group, any isomorphism from Z6 to itself will have to send a generator to a generator. Well, what are the generators of Z6? They're 1 and 5. And so therefore, really I only have two options for how to make an automorphism, an isomorphism from one of these groups to the other. The only choice I have is to send, where do I send phi of 1? Where do I send the generator 1? Because I have to send it to a generator. One option is I could send it to itself. 1 gets sent to 1. If I send 1 to 1, then, according to the homomorphism property, I also am going to have to send 2 to 2, 3 to 3, 4 to 4, 5 to 5, of course 0 to 0 because it's the identity. And so, when I send 1 to itself, the function that I get is the identity function. And that's an important automorphism for a group. It's not always the only automorphism for a group, but it is certainly an automorphism. So we know for sure that the automorphism group of Z6 has an identity element. That element, remember, is a function. It's the identity function. All right, so what if I make the other choice? What if instead I choose to send 1 to the other generator, 5, for Z mod 6? If I send 1 to 5, then I have to send 1 plus 1 to 5 plus 5. And in Z mod 6, 5 plus 5 is 4. So 2 would have to go to 4. For the same reason, 3 would have to go to 3, 4 would have to go to 2, 5 would have to go to 1. So the picture of kind of what this isomorphism is doing is it's kind of just reversing the order around my clock face. Right? If I send the clockwise generator 1 to the counterclockwise generator 5, then I still get an isomorphism from this group to itself. It's just somehow a reflection, in a way. It's sort of turning the clock backwards. It's the same, by the way, as the function psi of x equals minus x mod 6. Right? After all, minus 1 and 5 are the same things in Z mod 6. And so that gives me a second function, which is not the same as the identity. But at this point, we know that we're done. These are the only two automorphisms of the group Z mod 6. Why? Because any automorphism of Z mod 6 has to send generator to generator. And since there are only two generators, and because my function has to be one-to-one, it will be defined entirely by where I send 1. And there are two choices of where I can send 1. I send it to itself, and I get the identity function, or I send it to 5, and I get this opposite function, psi of x equals minus x mod 6. And therefore, the automorphism group of Z mod 6 is a group of two elements, and therefore, it in turn is isomorphic to Z mod 2. The identity element and an involution. After all, this function psi of x equals minus x is an element of order 2. Check it. Psi applied to psi of x is minus the quantity minus x, which is equal to x, and so that composition of that function with itself is the identity function. So the automorphism group of Z mod 6 is congruent to Z mod 2. And just as a parting shot, how might we use this to generalize what we just learned? So the observation that generators must get sent to generators actually will permit us to show what happens with Z mod n in the general case. What is the automorphism group of Z mod n going to look like? Since I have to send a generator to a generator, each automorphism will be determined entirely by where I send the generator 1. But there are going to be as many places to send 1 as there are generators of Z mod n. And there are as many generators of Z mod n as there are multiplicative units mod n. And so what we can prove is that the automorphism group of Zn is actually isomorphic to the multiplicative group of units mod n. Aut of Zn is the same as Un. The argument of sending generator to generator shows me why this is a bijection, why for every choice of a generator mod n, I can define an automorphism. What I haven't shown is why they compose together in the same way that they multiply in Un. That's something that if you're going to do a proof of this statement, you'd have to go into some more detail on. But at least I think we have sort of a heuristic argument here for why Zn has as many automorphisms as the multiplicative units mod n. So this is really just an illustration of how things get even richer when I can take a group like Zn and study its group of automorphisms, which can be very different from the group itself. And there can be many non-trivial, not identity function automorphisms from a group to itself. And that really, again, because the automorphisms of a group are also going to be a property invariant under isomorphism of that group, we can also use the automorphism groups of a group to study sameness and difference and to be able to spot the differences that matter. So that's a wrap-up of this chapter. We've seen what automorphisms and isomorphisms are, where do they come from, motivated by the desire to show that two groups are the same, so that we can get better at spotting the differences that matter. Isomorphisms preserve all the important properties of elements in a group, all the important properties of subgroups of a group, and we can always construct an isomorphism from a group to itself, that is, an automorphism, by conjugation, creating what's called an inner automorphism. And in any group, a set of all of its self-isomorphisms, all of its automorphisms, forms a group in its own right called the Automorphism Group of G.